How to find the inverse of matrix. So in this video we will continue talking about actions with matrices. Specifically, we will learn to find the inverse matrix. What is an inverse matrix? Let's provide an analogy. So if we take 5, let's say number 5, the inverse of 5, it's going to be 1 over 5, right? Or we write down 5 to power negative 1, correct? So if we take and multiply these two inverse to original number, we are going to get 1, right? Or the same way, 5 times 5 to negative 1, we are getting 1, yes? With matrices, everything is similar. The product of matrix A, if I multiply the product of matrix A by its inverse, it's going to be equal identity matrix. So this is important thing, so I highlight them with a red color and we move it here. We call it I, identity matrix. Just like we had multiplying number by its inverse, we would get 1. The same way, once we multiply matrix by its inverse, we will get identity matrix, which means identity matrix when we have ones by diagonal. Make sure you won't confuse with diagonal matrix. Diagonal matrix can have numbers by diagonal. Identity matrix can have only ones, numbers 1 on diagonal. Okay? All right. So, there are two main methods for finding the inverse of matrix, using algebraic complements and using elementary transformations. So we will go over algebraic complements. That's the easiest one. Let's start with considering matrix A as a square matrix. Matrix A consider as a square matrix. Okay, the inverse of this matrix, it's going to be A to power negative 1. We already know that. And the inverse matrix of A to power negative 1 we can find by using following formula. A to power negative 1, A to negative 1, rather saying, is equal 1 over determinant and multiply by A transpose. Transpose matrix. So the concept of an inverse matrix exists only for square matrices. Okay? One more time. The concept of inverse matrix exists only for square the matrices. If the matrices are not square, you cannot find inverse matrix because it's simple, it doesn't exist. Square matrix, it's we call the matrix when row and column have the same amount, like size is 2 by 2, 3 by 3, n by n. Okay? All right, so let's use it example 2 by 2, starting with the easy case. Matrix A is equal 1, 2, 3, 4. Okay, so first we need to find, step number 1, we need to find the determinant. Step 1, find determinant. So determinant for matrix 1, 2, 3, 4 is equal 1 times 4 minus 2 times 3. Who doesn't remember, I have a video where I show how to calculate determinant. So we are multiplying by diagonal practically 1 by 4 and then 2 times 3 and subtract. Okay? And this is equal 4 minus 6 equal negative 2. Okay. Very important note, very important. If determinant matrix of the matrix is equal 0, then the inverse matrix does not exist. Simply because here we divide by the determinant A. So our determinant A cannot be equal 0. It's the same thing over and over. Division by 0. We cannot divide by 0. That's because division by 0, it's giving us undefined value. So we mark down that the determinant cannot be 0, because if it's equal 0, then inverse matrix does not exist. Okay, we have negative 2, it's not 0, we are good. Moving to step number 2. Step number 2, we need to find matrix of minors. Matrix of minors. Minus M. The matrix of minors has the same dimension as the matrix A. So what is matrix of minors? It is, in this case, it's going to be M, because we mark down as a M, that we are going to fill up with elements of our matrix. But how we are going to do that? So back to our original matrix, A is equal 1, 2, 3, 4. So we are going to fill out this matrix of minors. First, let's look at top level left element. How do we find its minor? So we are going to scratch. You can scratch in mind, but right now I wanna show you. Okay, so take first element. Okay, cross out the row and the column which this element is located. Okay, and we have 4 left. So this 4 is coming to, we are filling this 4 in the matrix of minors. Okay, next. Consider next the following matrix element. Now we are taking next element too. Okay? we can mentally cross the row and column which this element is located. So we have left there 3. Okay, so from here, M, it's where placing in the row 3. Next, one, two, three, 4. Next, we are taking 3. And again, crossing. And we have left 2. So this 2 is filling out the second row, first column. And lastly, the last operation, oops, four, circling. I'm just going over quickly because you already understood what I am doing. And I will get matrix of minors for 3, 2, and 1. Okay, so we got it. This is a matrix of minors. Of the corresponding elements of matrix A. Corresponding elements of matrix A. Okay? Step number 3. Find the matrix of algebraic complement. Matrix of algebraic complement. Okay, so this one is very simple. All we have to do, change the sign of 2 numbers. So M, when here we have 1, 2, 3, 4 stars, because we are exploring 2 by 2, right? And we are going to change the sign of these 2 elements, this and this. Okay, so which means it's going to be, in our case, A is equal, A complement, let me put this way, AC complement, it's going to be 4, 3, 2, 1, and I'm changing sign, plus will become minus, a matrix of algebraic complements of the corresponding element of the matrix A. In step number 4, we are finding transposed matrix. Transposed matrix. Transposed matrix, to remind you, you can find in my previous videos where you the columns, the rows represent as a column, okay, and that will become transposed matrix. So let's see. For my A complement, that is equal 4, negative 3, negative 2, and 1. Okay, so what am I doing? This 4, negative 3, that's a row. I'm going to represent as a column. So our transposed complement matrix is going to be 4, negative 3. And then, let me highlight on this. And then with the green color, negative 2 and 1, it's going to come as a, actually, I will do much better way. Hold on, I'll do better way. What did I have here? 1. This is what I will do. Negative 3, highlight and let's say blue color, and negative 2 and 1, I will highlight them with green color. Okay, now 4 and negative 3 become our column, and negative 2 and 1 will become second column. There we go. This is much better. Okay, so this is transposed matrix. Transposed matrix of algebraic complements of the corresponding elements of matrix A. So we have prepared all elements. We've found out our determinant. We found out transposed matrix of the complement. So the inverse, so final answer, number 5. The step number 5. So just to remind you, inverse is equal 1 over determinant of A times transposed of complement, R, transposed of complement. So what do we have? Inverse, it's going to be equal. Our determinant, how much was it? Here it is, negative 2. So we are going to have what? Negative 1 over 2, right? And our transposed is going to be four, negative 3, negative 2, and 1. And that's it. The answer is best left as it is. You do not need to divide each element of the matrix by 2 as you get fractional numbers, because not all of them are dividable. So this part, when we get by division, by multiplying fraction, we get some fractional portions. I will discuss in separate video, okay? All right. Now, how can we make sure? As we know, in algebra, we always can check the answer. How we check in this case? Okay, this is where our identity matrix come into play. We learned that original times by inverse is equal identity matrix. Again, identity matrix, we get ones by diagonals, and the rest is going to be 0. Let's do that. So, times A inverse, it's going to be our original matrix is, already forgot, let me see, 1, 2, 3, 4, okay? It was pretty easy to remember. 1, 2, 3, 4, and we multiply by inverse times negative 1/2 and times 4, negative 2, negative 3, and 1. Okay, let's see what we're going to get. Negative 1/2. So I'm getting the following, multiplying this 1, multiplying by this 4, right? And then these 2 multiplying by these 3 and adding them up. Okay. 1 times 4 plus 2 times negative 3. Okay, now second row, what I'm going to do, I'm going to take this 3, multiply by this 4, and then plus this 4, multiply by this negative 3. Actually, I could, yeah, no, it will be mess. So it's going to be 3 times 4 plus 4 times negative 3. Okay, so next, now let's work on second column. What we are going to do, we are going to take this 1, multiply by negative 2, and 2 multiply by 1. So the row of the first we multiply by column of the second. And we are getting 1 times negative 2 plus 2 times 1. And the same way with second case, 3 multiplied by negative 2 plus 4 multiplied by 1. So how much we're going to get? Negative 1/2. This is going to be negative 2. Second one is going to be 0. So 0. And this one is going to be 0, right? And the other one, negative 2. Which is going to be, if I multiply by negative 1/2, every single element, I'm getting 1, 0, 0, 1, which is equal identity matrix, which means our matrix is correct. The inverse matrix we calculated correct. All right. This is the end of this one, and then I will record the second one with 3 by 3 matrix, okay?